So, operating system operations. First, you have the Bootstrap program, as you can see. Here it is. We talked about it. It's simple code that is stored in an ROM, basically, that initializes the operating system. So it basically loads the kernel, okay? Then the kernel loads. When it does, you start the system daemons. Those are services provided by the operating system, okay, by the kernel, but they're not part of the kernel. So you can start something like the TCP/IP. You can start, whatever that is not inside the kernel, but you still need it to be loaded. You tell me, how about those that are inside the kernels? Of course, they're being loaded without the need to say so, and they remain loaded and running all the time. Like memory management, as I said, like, whatever, component that belongs to the kernel. Then we have two kinds of interrupts that keep working. The hardware interrupt, it happens by one of the devices if needed. And the software interrupt, which is a trap exception for those who studied higher level language like Java or Python. You know what an exception is. A trap is an exception, by the way. So a trap would happen if, you have a software error like dividing by 0 as an example, okay? Or you can also request for operating system service, system call. So you need here an interrupt, okay? So this is an interrupt with a trap, an error that happened. This is an interrupt based on your request. You need a system call. And it happens all the time, by the way. It happens all the time. And whenever you want to print something into the screen, whenever you need to read something from a file, whatever, all those are nothing but system calls inside the operating system that work as services that you can use, right? And based on that, each and every one of them, you generate an interrupt. If you have other process problems, include infinite looping, okay, or you have, invalid access, like, processes modifying each other or something, that would also generate an interrupt. All right, now, how do we execute programs? In what manner? We have the oldest programs, like computers, that used to execute one single program at a time. One single program at a time. Like the original versions of DOS, as an example, disk operating system, MS-DOS. Okay. They used to be single program operating systems. What does it mean? If you have program 1 and program 2, if you run program 1, you cannot run program 2 until you exit program 1 and then you run program 2. So you cannot really have more than one program running in the same exact time. Okay, of course, in DOS, we used to hack that in the 90s by having something like, it was called terminate and stay resident, TSRs. I used to program that all the time back then in the 90s, TSRs, which, they literally override the mechanism and, keep switching between two programs. If you want a watch or something to appear in the, here in the top right side of the monitor, then you used to write it literally as a virus. We call it TSR, terminate and stay resident. So we wrote viruses in order to do something that you have now for granted. you know, and they used to, keep switching between the two programs all the time. That was early 90s. All right. So that's the single program computer. So what about multi-programming? Multi-programming is when your operating system loads many different programs in memory in the same time. P1, P2, P3, P4, P5. Say they literally coexist. They literally coexist in the same time in memory. Okay, which one would run first and so on? This is a schedulability problem that we will, intensively talk about later. But for now, we need to know that multi-programming means loading more than one program in memory. Okay. Earlier versions of an operating system called MS-DOS, which is the origin of Windows, that we used in the late 80s, early 90s, it was a single one. So in memory, you have one and only one program beside the operating system, of course. Okay. So the multi-programming organizes jobs. Okay. What is a job? A job is code and data combined together. Okay. This way, the CPU always have one to execute. I'll talk about that, but before I do, those kind of programs are called jobs. Some references in operating systems, they do distinguish between a job and a program. Okay, for this book that I'm talking about, okay, or I'm using as a reference, the authors used job and program, exchangeably. So they mean the same thing whether they say a job or a program. Okay. A subset of total jobs in system is kept in memory. And the others, they exist somewhere. Okay, we call it the virtual memory. We're going to be talking about it later. One job selected and run via job scheduling. Job scheduling. We need to say what a scheduler is, right? And the word scheduling means assigning priority mainly, so that's what a scheduler does. So it says, we're gonna be executing P1, then P4, then P2, then P10, and then P5. So that would be a schedule, okay? We don't give this randomly this way, the way I said it. No, there is basis behind this, okay? And for those who studied data structure and you dealt with the queuing systems, you know that we have something called first come, first serve. We have something called sorted job first. We have something called, earliest job first, and so on and so forth. We have a lot of different algorithms that we can use for job scheduling, and each and every one of them has a criteria to judge upon, to say which one is going to be executing before which, and every one of them will have a different schedule. So, of course, since we have different criteria of judge, then, we have different schedules or different sequence to execute. When job has to wait, okay, for an I/O as an example, OS switches to another job. Why? Let's take an example about this. Let me just make a space here. Okay, so let's say you are in McDonald's in front of the cashier. Here it is. So this is the cashier. And we have people waiting in line to be served by the cashier, okay? This cashier is our CPU, by the way, okay? And then this one, okay, accompanied with a friend or sibling, found out as soon as they reached the cashier, that one found out that that one doesn't have the wallet on him. Okay? So, this one decides to send the sibling or the friend or whatever home, bring the wallet and come back. Okay? During this process, for this person to go home, bring the wallet or take the wallet and come back to pay, what do you think is better, system-wise? For this guy to step aside and give a chance for the rest of the queue to be served by the cashier, or for this one to wait in front of the cashier, okay, until the other one comes back? Of course, the second option is not an option. The second option is not an option. The better one is for this one to step aside, give a chance for people to be served, all right, until this one comes back. And when this one comes back, the original one that was waiting will take its turn again. You tell me it's going to be waiting in queue again? Well, that depends on the scheduling technique, okay? But it will be judged again. It will be assigned a priority again. This priority could be the highest, according to some scheduling algorithms. Others will assign it a normal priority, and so on and so forth, okay? So based on this example, we know that, when the job waits, it steps aside, okay, until, whatever it's waiting for happens. Let's say an IO request or whatever, okay? I hope this is clear. Now we have multitasking. Before I talk about multitasking, this multi-programming is called batch system. Okay, and usually those kind of jobs are being, executed in order, first come, first serve, or, But the thing is, the whole job is being executed fully, and then the next one, and then the next one, and so on. The multitasking is an enhancement. It's an enhancement for the batch systems. Okay, what is it? The fact here is that the jobs will not wait here, being executed, until, it's done. No. Instead, it will keep, changing its position. So let's say process 1 or task 1 now is going to execute for 5 seconds. Then P2 will execute for 7 seconds as an example, or whatever, or maybe equal time sharing. P3 will execute, and so on. And then P1 will execute again and again and again until all of them are done. Why is this? To give a feeling of interactive behavior, okay? The sequence, doing it in sequence, P1 finishes, so batch processing, gives the feeling for later processes that are not being dealt with. Okay, so P1 will finish, and then P2, and then P3, and then P4. So how about P100, right? It will keep waiting, and the process will realize that it's not being served. So instead of that, we're going to be giving everyone a quantum or some time, okay? Well, if P1 finished in this quantum, perfect, it leaves. If not, it waits for its turn again and again and again and so on. So we distribute the time. We call it time share. Time share. So a logical extension of batch systems, it's an enhancement, as I said. The CPU switches jobs so frequently that users can interact with each job while it is running. So you tell me, you know what? The user will realize still that they are waiting. No. It's not the case. Why? Because the speed of changing jobs is so fast that the user will not realize it. When you look at a fan, you have a fan with 3 pieces like that. When they are revolving very slow, you can see every piece moving. But in high speed, what happens? You see them as a single piece. You don't see anything that is being changed. That's exactly what happens. If you have this program running on the computer, even though the computer is changing programs, you will never feel it. You will feel that the program that you are using, is the one that is running all the time. Okay? We will see that later in chapter 5 in details. Now, this is how the operating system, the memory looks like. Here, this is location 0. Here's the max. Of course, I don't like how it's organized. The operating system should be in location 0 because this is the very first thing that gets loaded. Anyhow, you guys know the idea. And then we put processes like that. So you tell me, what is the process? You kept talking about jobs and programs. Okay, what is a process? A process to a program is like the soul to the body. Okay, so the body itself without a full soul is nothing, What gives the liveness, the motion, the thinking, the whatever is the soul, right? Same, So the process is a living program. It's a living program. So the program, when it gets alive, it becomes a process, okay? The program itself is nothing but the body, the lines of code written, okay? But when this one gets loaded and it's combined with a program counter and data and so on, they become a process, okay? So every process is a program, but not every program is a process. Okay? For those who studied object-oriented programming, you can see the process is an entity that inherits the program and adds to it. Okay? It adds to it liveness and data and program counter and so on and so forth. Okay, so every process is a program, but not every program is a process because some programs are not loaded yet into memory and therefore they are not processes. Okay, now for dual mode operation allows operating system to protect itself and other system components. How? Well, you have two modes. Look at that. You have something called user mode. What is user mode? It's the mode when you run your own programs. It's called user mode. And you have kernel mode. It's when the operating system takes control. So the user mode is a mode when the user has the control, and the user now can run programs, user programs. The kernel mode, however, is the mode when the operating system, when the kernel has the control, and therefore the kernel will run its own routines. And we have mode bit, okay, provided by the hardware. So it's a single bit. As you know, as engineers now, the single bit can be either 1 or 0. So 1 means user mode, 0 means kernel mode. So the user cannot run anything unless this bit is 1. Okay, so this provides ability to distinguish when the system is running, okay, user code or kernel code. When a user is running, mode bit is user. Of course, it's a bit, so it's a 0 or 1, right? So let's say this is 1. When kernel code is executing, mode bit is kernel. Let's say this is a 0. How do we guarantee that user does not explicitly set the mode bit to kernel? System call changes mode to kernel, return from core reset. What does it mean? Here, the danger here is for the user to try to hack the kernel by changing the bit to kernel mode while having control. Okay? So how this is being protected, you will see later in further chapters. So some instructions designated as privileged. Privileged means, something that, it's not something guaranteed, only executable in kernel mode, okay? And here is how it looks. Look at that. Look at this beauty. So you have here the two layers, as you can see. This is user mode with mode bit is 1. And here is the kernel mode when the mode bit is 0. So the user, runs a process. Then the user needs a system call. The user wants to print something, the user wants to read some file, whatever. So the system will change the mode bit to be 0, to be the kernel mode. Only after this is done, the kernel will run the service. Then what happens? After the execution is done, the kernel will change the bit to be a 1 and return data to the user. Okay, so the system call will basically return a result to the user. So I hope this is very clear, and how the moving from a user mode to a kernel mode occurs.